Hello, everyone. My name is Qianxiao Li from National University of Singapore and also Institute of High Performance Computing in Singapore. So thank you for tuning into the video where I'm going to talk about my recent work together with my collaborators on analyzing the mathematical aspect of learning dynamics using RNNs, recurrent neural networks, and in particular trying to uncover the relationship between learning and dynamics, especially in the context of memory. So this is joint work with Weinan and Jiejun Han from Princeton, as well as Li Zhong from Peking University. Without further ado, let's begin. So to provide some background, if you look at the interaction of machine learning and dynamical systems, you can roughly classify them into three categories. The first category will be machine learning via dynamical systems. So this is where we apply dynamical system tools like control, numerical analysis, or more general Monte Carlo methods to try to understand certain aspects of deep learning, like how to optimize deep neural nets and how to perform architectural search, design, or generalization error estimates for deep learning. So that's some examples. Of course, there's many other examples as well. And the next class of problems will be machine learning of dynamical systems. So this is where you actually have an underlying dynamical system that you probably maybe only have observations of, right? And your goal may be to learn this system, or maybe you already know what the systems look like with a few parameters, or many parameters, and your goal is to identify what the system is. Okay, so for example, system identification, especially in the linear case, is very well understood. And of course, you can also have model reduction problems where you actually observe the system and you don't need to recover the system because you know the equations. For example, you know the PDEs. And what you want to do is to reduce the model into maybe ODE. In this case, you want to find another reduced order model for this. So those fall into the category of machine learning of dynamical systems. And machine learning for dynamical systems, in some sense, a little bit different, that we have maybe input and output temporal data that may arise from some underlying dynamical system or may not, right? And our goal is to design a machine learning method that learns such relationships that may arise from a dynamical system. So these are not, the actual dynamical systems. For example, time series forecasting classification, the time series could be generated from dynamical system, but you do not observe the entire thing, right? You only observe parts of it, the observables, and then you're trying to predict the observables as response with some input forcing. So in this case, this also includes sequence-to-sequence models in, let's say, in translation. And all of this, it requires some interactions of dynamics and learning that is not really to recover some system, but really to model certain aspect of the system. So we call this machine learning for dynamical systems, and this is going to be the focus of today's talk, in particular with recurrent neural networks. Okay, so what's so special about learning dynamical relationships? So everybody knows supervised learning is about learning to make predictions. You have some data set that contains some inputs and outputs, like pictures of cats and dogs, and then you have some outputs that's just labels. And your target here that you're trying to learn or approximate is just some function that maps each of this picture into a label. Okay, and then the goal is to learn this target function f star using some information from the data set. Now this represents a static setting, but very often supervised learning has to be performed in dynamical settings. For example, as we said, price forecasting, right? You're given some past price, you predict tomorrow's price, and you have to do it, every day from tomorrow onwards, say. And similarly, it goes for machine translation. You need to translate a sentence, let's say word by word, but given the entire context of the sentence. And finally, if you want an application that's more flavored towards dynamical systems and maybe science and engineering, you have some, force system that's given some temporal forcing. It's going to have some response, and your goal is to just measure the forcing and the response and try to form a model between them. Again, the response is not going to be just dependent on the forcing at this instant, but maybe it depends on the forcing of all past instances. So what's common about all of this problem is that each output here depends on a sequence of inputs, just not just one input, but rather a sequence, right? So this could be a sequence of all the prices in the past, or a sequence of this entire context sentence, so on and so forth. And also we need to model not just one input-output relationship, but a sequence of such relationships, right? So for example, the tomorrow's stock price is going to depend on all of my past prices, but the day after tomorrow's stock price is going to depend on all the past prices and also tomorrow's price, right? So on and so forth. So you have a sequence of input-output relationships. We'll make all of this mathematically precise, of course. Okay, so in a nutshell, what we're trying to investigate is how these temporal sequential structures actually give rise to very interesting interactions between dynamics and learning. So let's look at this setting in more mathematical detail, right? In the static setting, the input is just some vector. Okay, and the output is going to be a vector too. For classifications, n will just be the number of classes. And if you're talking about regression problems, which we'll mostly focus on today, n is just going to be 1. And the target is just basically some function f star that gives you output y given some input x. Okay, but we say that in the dynamical setting, things are a bit different. For example, the inputs here is not going to be just one vector, but really a sequence of vectors, xk, parameterized by this index k. And finally, of course, the output is also a sequence, right? And the target is no longer just one function, but a sequence of functions. And this function is not an instantaneous function. It actually depends on this entire input sequence. Okay, so this is a very general function that depends the entire input sequence. Now, of course, you can also have additional structures to this. Which part of the sequence does this function depend on, right? For example, causal features. We're going to talk about that later. So to compare, the goal of supervised learning is to learn and approximate a single f star. But in the dynamic case, we really want to approximate a sequence of h stars. Okay, so how we do that, one very well-known way to do it that has been invented for a very long time is to use recurrent neural networks. So you haven't seen recurrent neural networks. It is a way to generate, in a nutshell, a sequence of functions. Okay, so what we do is basically taking the input sequence xk, okay, and perform linear transformation of it, and conveniently defining hk, which is called a hidden state. And this hidden state forms a dynamical system, a discrete one here, such that it transforms this h using some matrix w, and also transforms this x using u, add them together, apply some nonlinear activation. So this is just a one layer of neural net, and then get the next hidden state, and so on and so forth. Okay, and then our output is going to be, so the convention is that the initial condition is 0, but of course there are cases where you want to set the initial condition to something else. Now the output is just going to be a linear function of this hidden states. This is in the simplest case where the RNN only has one hidden layer. Of course, you can add another layer here. There's a nonlinear transformation, but we're going to stick with the simplest case. So pictorially, what happens is that you basically define a hidden state that runs through time. And each time is going to take a x0, the input, and give you output. Now, in the language of dynamical systems, this is really a forced dynamical system, right? X is a forcing, and you construct basically this hidden state as parameterizing some hidden force dynamical system. And what you can see is that each RNN actually parameterizes a sequence of functions for k, increasing. For example, hk is just a mapping between x0 all the way to sk minus 1 to y hat k. Right? For example, the y3 hat is going to depend on not just x2, but also x1 and x0, and the dependence happens through this evolution or forward propagation of this h. And of course, as you progress further, you get another function or another function, another function and another function. So this is a sequence. So what is training RNN? Training RNN is just to adjust this weights, C, W, U, so all of these parameters, so that your sequence of RNN parameterized functions is going to match my ground truth sequence. Again, my ground truth is a sequence of functions, not just one function. Okay, so from the outset, as we said, the RNN approach actually parameterizes not just one function, but a sequence of high-dimensional functions. Actually, the domain of these functions actually increases as you increase time. Okay, at least doesn't decrease. So therefore, the sequence of functions that can be approximated this way, right? They should contain some structure. Okay, so because they are not all independent, right? This sequence, it has to contain some structure. In some sense, this is a little bit like a reverse of the Maurice-Wansink formalism in statistical non-equilibrium statistical mechanics, where here they take a partially observed but a Markovian system, so instantaneous system, and then because I only partially observe, in fact, in the formalism, you are interested in only a part of the system. Then you can actually transform it into a fully observed autonomous system, but with memory. Okay, so RNN in some sense is doing the reverse, right? We have a fully observed system with memory, right? For example, the dependence of tomorrow's stock price is going to depend on the entire history of stock prices. And what RNN does is to then change this or approximate this with a partially observed system, but it's Markovian. That means we construct some hidden system that's not observed, H, such that to make the entire system Markovian, and that is an interesting way to parameterize a sequence of functions. Okay, so with that, we define this RNN hypothesis space. And so then what kind of mathematical questions do we need to answer in order to really gain an understanding of what's RNN doing when it tries to approximate the sequence of functions? Now, here's a generic picture, right? So essentially in machine learning, we start with some hypothesis space, let's say RNN hypothesis space, and we have started with some target. So this target could be just one function in the static case, or a sequence of functions in the dynamic case. So the first question we can ask is how big is the approximation space? If I were to find the best possible model in my space, how far is it away is it from our target? And this is called the approximation error. But this is not the entire story, because even if this is very small, it doesn't tell you how you actually can find a model, right? You can actually learn a model. So the learning is actually optimization or training, right? So you start with some initial guess, and you try to go towards the best model and using the data set, training data set, say. And this is your learned model from the training data. So now it comes an important point that there is always an optimization error, because this empirical risk minimizer will be the best possible model you can actually train by solving your training problem, the empirical risk minimization problem. Because there could be difficulties in optimization, let's say due to non-convex or due to some other features that we will observe later on, there's always an optimization error. So why is this 2 points not the same? It's because the empirical risk minimizer is not the best possible model because your data set is finite, right? So there's always a finite data phenomena, and the difference between this is called the generalization error. So you can see that from the learned model to the target is really a combination of 3 errors: approximation, optimization, and generalization. And to really gain an understanding of a particular machine learning method, one really needs to understand how does it interact with all of these 3 aspects of learning. So our overarching goal is to really precisely analyze, okay, what's really new in a dynamical setting in RNNs when it comes to these questions. And we're going to mostly focus on approximation and optimization questions today. Now, to do some precise analysis, we need to do some simplifications. So we're going to introduce the following idealized scenario. So we're going to take the linear activations, and we're going to take continuous time. That means instead of using a discrete dynamical system, we're going to idealize it as a continuous dynamical system. Okay, so the reason why we want to do that is it may appear simple, but we will see that the key features of the problem is actually preserved. So what is the key feature really? We said that the key feature is really on 2 fronts. One, the model, the RNN model, is dynamic, right? It produces a sequence of function candidates, right? Or functional candidates, as we later will see. And then the target is also described by some dynamical phenomena, right? So in one word, dynamics is really what's new compared to the static setting. And even when we go to the linear case and we go to the continuous time case, we still preserve this dynamical aspect. Okay, and what's nice about going to this linear and continuous time case is that key properties such as regularity and memory, something you see all the time in the practical literature about how that may affect RNN training, or some theoretical work as well. This allows us to actually place all of these terms in precise mathematical language and also simple mathematical language, so they can be precisely formulated. So this is probably overarching theme in a lot of theoretical work in this area. And this allows us to perform more or less complete analysis, at least in the approximation case, to highlight the key issues that's different in dynamics. Okay, so this gives you an idealized scenario that is a good playing ground to gain some first step understanding. Okay, so let's introduce the continuous time formulation. We start with the input and outputs, right? So the input space now, instead of a discrete temporal sequence, we're going to consider it as a continuous time temporal sequence. So this is just a sequence of the space of continuous functions that vanishes in infinity, right? So this is just, so the vanishing in infinity just makes the whole function space more well-behaved. So each member of our input space is just going to be a sequence in this time indexed by time. So it's a path in RD. Okay, so of course this is a Banach space, so we can define the usual supremum norm. Okay, similarly, output space, we're going to also think of it as a path, right? So this is a continuous and bounded functions. From R to R, we're going to consider regression problems. So there's only one output dimension. And finally, what is our target? The target, because now we're considering this trajectories, right, functions. So the target is going to be a sequence of functionals, each of them called H star T, which maps your input sequence, which is this space, to some real number R, such that YT, for each T, YT is just going to be the result of it, applying H star T to your entire sequence X. Okay, so this is a functional in the strict sense. Okay, so with that said, what is the linear RNN hypothesis space, right? This is just replacing the usual RNN with the continuous time approximation, well, idealization. So we will have a continuous time ODE where, if you have seen this RNN, this is the usual nomenclature. So H is going to be the hidden state. W is the recurrent kernel. U is the input kernel because they deal with the recurrent part of the network and also the input part. And finally, C is the vector of output layers. So M here is the size of my hidden dimensions, right? So the bigger the M, you can see that the more powerful this RNN could be, but it's also more expensive. So this, we can summarize the linear RNN hypothesis space as this object. Okay, so first of all, let's just focus on this equation. So what is this? This is just the exact solution of this problem because this is a linear ODE. We can solve it explicitly as an exponential function here. And yeah, so we can, this is the exact solution. And of course, WUC is something you vary on this hypothesis space. And each member of this hypothesis space is going to be an entire sequence of functionals parameterized in the RNN solution. So again, for each choice of parameters W, U, and C, you actually give rise to not just one functional, but a sequence of functionals indexed by time. Or you can also think of it as a linear operator. Okay, so we're going to do something more to assume that my W is going to be contained. I mean, W only has negative eigenvalues. So the eigenvalues real part is negative. The reason for this is that we want the RNN to be stable. So when you evolve this system, it does not explode, right? So that's why we consider this negative real parts. Okay, but you can get arbitrarily close to zero. So you can also not decay, right? I mean, decay as slow as possible. Okay, so with the definition of hypothesis space, the key question we want to answer in this talk is what sequences of functionals can actually be approximated by those in the RNN hypothesis space, and how does this approximation happen when you actually train it as using GD? So the first question is approximation. Second question is optimization. Okay, so we start with some approximation theory. What are the key approximation problems you can pose? There's two of them. The first one is a universal approximation property. It just says, what kind of functionals, okay, can you approximate using RNNs to arbitrary precision? But this is not enough. In some sense, the more important question is what kind of functionals are well approximated? Let's say using a small number of hidden states, because hidden state is the thing that controls the complexity. Very importantly, we want to make a note that we are not assuming that the target functionals, the target family H star, are generated by some underlying dynamical system. Okay. In other words, there need not actually exist any dynamical system for which H star is going to be YT, where YT is some nonlinear, possibly, function of H, and H is a forced dynamical system. Okay, we do not assume that this is the case. So this is, in contrast, a lot of prior work on either approximation or approximation or optimization of neural nets, where this is the setting that's being considered. So this setting, you can think of it as a little bit like a system identification, in that there's an underlying system, and your RNN is just approximating these systems. So in that case, the approximation results becomes more like the neural network approximation results that you see in the feed-forward case, because you just need to approximate F and G with your RNNs. But here we have to consider a different case. We want the approximation to be stated precisely in terms of these functionals, okay, and not some underlying representation. This representation need not exist. Okay. But of course, these functionals cannot be arbitrary. They must have some structure. We'll see why they must have some structure. Okay, so to do that, we have to introduce certain classes of functionals. What does it mean, right? So the first functional we want to introduce, first class of functionals is the so-called causal functionals. So causal functionals are where a functional, depending on t, it does not depend on the input values at a later time than t. Okay, so if you have two input trajectories that agree up to time t, then their functional value must agree. Okay, so these are called causal functionals. Why do we care about causal functionals? Is the simple observation, if you take any functional parameters by the RNN, linear RNN, right, which we have this exact solution, then this has to be causal, because it doesn't, as you can see, RNN does not depend on the future, at least, unidirectional RNN does not depend on the future values. Okay, so that's obvious. The second one is continuous linear functional. This is again a simple definition. So functional is continuous and linear if linear basically just says that it acts linearly on these trajectories, and it's continuous when this is norm. So the action h here, there should be absolute value here, should be smaller than infinity. Okay, so once this is true, we can actually define the induced norm, the usual dual but not dual norm with respect to our usual norm on X. Okay, so this is standard. Again, why do we care about continuous linear functionals? Because every linear RNN functional is continuous and linear. Okay, so linearity is trivial because this is just a linear operation on X. And then continuous because we have assumed this is W has negative real parts. So this exponential is bounded from above. Okay, so this is continuous. Okay, so now we go to some other classes. So this is more of a technical requirement. A regular functional. So what are regular functionals? Okay, you can read this, but what it says is actually something simple. If you have a sequence of paths, okay, each of them converging to 0 point-wise in time, then your functional values limit should also be 0. Okay, so in other words, the regular functionals are those that do not depend on the value of a path on an infinitesimal support, right? So that's reasonable. And again, we observe that by dominated convergence theorem, every RNN functional is going to be regular. So there's no problem. And finally, this is a property that does not just apply to one particular functional, but actually a family of functionals. So we say a family of functionals here is time homogeneous if this symmetry condition is satisfied. So what it's really saying here is that there's no special point in time. That means if I take my functional, okay, my sequence of functionals and my input sequence, I shift the input sequence and the functional in my sequence of functionals by the same amount, then the value, the output, right, will be exactly the same. Right, so we can shift them together. And again, we consider this because every linear RNN functional sequence is actually time homogeneous. Okay, this is because if you look at the exact solution of the RNN, linear RNN, this is the convolution form, right? It's the convolution between this vector and this vector. And because convolution is shift invariant, so this will preserve this invariance. Okay, so this is also straightforward from the RNN formulation because the weight of the RNN does not depend on time, right? So you use the same weights over and over again, so therefore there's no special point in time. Okay, so to summarize what we said before, there is some restrictions on the entire RNN hypothesis space. Okay, so first of all, it has to be continuous and linear, and it's causal, it is regular, and it's time homogeneous. So this is what we said. Okay, so I want to make a remark that many of these properties also holds for nonlinear activations, right? So actually, other than linear, most of this, so causal, regular, and whole time homogeneous holds for even for nonlinear RNNs. Okay, so this is not just for linear. So this is a good setting even in general. Okay, so the approximation theory. Here's our first main result on approximation theory. We showed in previously, right, any functional that can be parameterized by a neural network. So the neural network, you can think of it as a RNN functionals. They must be continuous, linear, causal, regular, and time homogeneous. Now, our first main result is a converse, in some sense, to this statement, which basically says that any family of continuous, linear, causal, regular, and time homogeneous functionals, so any functionals that satisfy the restrictions of H hat, okay, can be uniformly approximated by RNNs. Okay, the approximation is uniform in T, and is also uniform in X, my input signal. Okay, so this is kind of a result that maybe is obvious, but maybe it's not so obvious in that even if I do not assume my target family of functionals actually comes from some linear dynamical system. Of course, if it actually comes from linear dynamical system, then there's no need to prove approximation. It's equal, right? But even if it does not, we have an approximation, uniform approximation to arbitrary accuracy, as long as you take the number of width in large enough. Okay, so the number of the hidden states large enough. And the approximation is uniform. So in some sense, you actually construct a same set of weights that approximates this entire sequence of functionals together. Okay. Yeah, so I will not discuss too much about the proof, except that maybe I will just say that this is a consequence of the Riesz representation theorem with polynomial, with exponential sum approximation. Okay, you can see the paper for details later on. Okay, so in some sense, that's the universal approximation theorem is a basic result, right? But it's not a very useful result when we're trying to understand, precisely what's easy and what's difficult to approximate. Okay, and this is our goal next. It turns out that different functionals, you can think of it intuitively. They should be, some of them should be more easy to approximate than others. So for example, if we consider input signal here like that, okay, and we feed it to a class sequence of functionals, and then it will give me some output sequence. Okay, so in this case, this looks like a nice class of functionals because, first of all, the output behaves, quite smooth, so it depends smoothly on the inputs. And moreover, you see that after the halfway point, when the input starts to saturate and give you no more information, this YK also starts to saturate. So in some sense, it tells you that it's really not responding to information very far away. So in some sense, its memory is low. Okay, so it's smooth and it has small amount of memory. And now if you take the same input and you consider the second system where the output looks very chaotic, right? So here, one is that the output does not depend very smoothly on the input. Okay, that's one. And number two is that you see even after the input saturates, the output still, moves weirdly, right? So actually all of this motion depends on the past inputs, okay, in some sense. So one would intuitively think that this is harder to approximate than this one, which is the case. Okay, so how do we put this more precisely in terms of mathematical terms? Okay, what we can do this is to try to make sense of what is smoothness in memory, at least one way to to characterize these notions. So what we're going to do is we're going to take the standard basis in RD, and we're going to take this boldface EI and define it as the constant signal. So this is a signal whose ith component, so ei, right, whose component is just a constant function in time for a positive time. Okay, so it's going to be a constant signal, something like this. Okay, and we're going to do that for each coordinate dimension. And then once we are given a family of functionals, we can now define the following, right? So we denote the output of this constant signal by yi. Okay, so this is the output of this constant signal when you apply this sequence of linear functionals or any functionals to ei. Okay, this input signal is constant in time. So 1. Okay, then the smoothness is going to be characterized, the smoothness of our functional is going to be characterized by the smoothness of this mapping, the yit. Okay, and memory is going to be characterized by the decay rate of this mapping. In fact, it's not decay rate of mapping itself, but decay rate of derivative of this mapping. So how sensitive it is to time. You can see that this is not very sensitive, but this one is very sensitive. Okay, so now we can state our approximation result. You can slowly try to parse this, but I'll just give the main idea behind this result. Okay, so we assume the same conditions as previous theorem. So we have this nice causal, regular, time homogeneous linear functionals, and we're gonna do 2 assumptions. Okay, so this is the first assumption, and this is the second assumption. So the first assumption is easy to see. The first assumption basically says that if I apply my functional on a smooth, actually a constant signal, then my output should be somewhat smooth, right? So this c to the alpha plus 1. This is the smoothness condition. Okay, so this is the alpha plus 1 times continuously differentiable functions. And the second condition, this combination of conditions, you can read what it says, but basically what it says is that the derivatives, okay, up to order alpha plus 1 of this constant signals response, okay, is temporal derivatives, has to decay with rate at least exponentially e to the minus beta. Okay, so e to the beta t is going to be some O1. So this is basically a precise definition of memory. Okay, that means we want the system to memory to decay with the rate at least e to the minus beta t. Okay, with that, then we can prove the following uniform approximation result. So this is the left hand side is the same, and the right hand side now has the explicit rate estimate. Okay, and of course this m is the width of my number of hidden states, the width of my RNN, and as you increase the width, this is going to decrease algebraically in the width. At least so it seems. Okay, but we will see that there's something more interesting you can say about it. Okay, so to understand the rate estimate, the smoothness dependence. Remember, alpha is a measure of smoothness of my functional. This is not so surprising. Very often when you take, let's say, Weierstrass approximations or various other Fourier approximations, this smoothness condition usually comes out, right? So the more smooth the function is, the faster the approximation is going to happen. Okay, so this is not so new. But the memory dependence, the beta and gamma part, okay, especially beta, is new. Okay, so to remind you, the beta basically says that the derivatives of this must decay, the derivative of this constant signal must decay like e to the minus beta for some beta greater than 0. So in this case, we don't have curse of dimensionality. That means that we don't have, even when D is large, this bound only scales linearly in D. Okay, this is a reason because we are in a linear setting. In linear setting, it's very well known that you can actually consider each dimension separately, right? And so the error bound is additive. However, hidden in this result is a very interesting point about curse of memory. And it might not be so obvious from this bound, but let me explain why this is the case. So the very important observation is that for the rate to hold, right, we need the derivatives of this guy to actually decay exponentially. But it is reasonable that we have to approximate functions that does not have this property. Okay? And this is precisely the problem that you can think of as having long-term memory. Let's consider example, right? So we take one-dimensional case. And then we take a h star, your target functional, as this kind of form, where it is basically a convolution between x t minus s, right, this x signal, and a kernel rho. Okay, so I said that assume this, but actually in the proof of the previous result, we show that there is always a representation in this case. So there always exists a rho such that you can represent the entire class of functionals, a sequence of functionals, because of all the time homogeneity and other conditions we assumed. Okay, so this representation theorem is a consequence of the Riesz representation theorem. Okay, so any functional can be written here, but we're going to assume that this rho is going to decay like this. So t to the minus 1 plus omega. Okay, so it's getting closer and closer to 1 over t. But it remains integrable. Okay, so this omega parameter, in some sense, controls the memory. As omega gets closer and closer to 0, the memory becomes longer and longer. And at precisely 0, you can see that the action of a constant signal will not decay anymore. Okay. So therefore, this is going to have the ht is going to have non-exponential decay in the signal, and of course all its derivatives will also have non-exponential decay. So it does not satisfy the rate estimate that we had before, right? So in this case, how do we actually obtain an approximation rate for these functions? These are perfectly nice functions. I mean, they are still decaying. They just don't decay exponentially. Okay, how these functionals? What can we do? The idea we can try to do is to truncate it. Okay, so we define a cutoff time t, and we define a new functional, which is generated by this rho tilde, which is just the original rho, okay, for our original functional, cut off at time t. And of course, we can do all the smooth, approximations to make this as small as possible, okay, so that it still satisfies our conditions. So once we have this cutoff, because we cut off at big time t, you can just take the integral and show that the estimate, the error resulting from this cutting off of h star to h tilde is about t to the minus omega. Okay. And then once we cut it off by h tilde now, because it's compact support, right? So it gets cut off after time t. So of course it decays as fast as anything. So then we can have an estimate. Okay, so we can use the previous one and have an estimate. Okay, you can check the derivation. So we get an estimate here that depending on the beta, which is a rate decay. And of course, we have to optimize over beta to find the best possible rate, decay rate that can still fit this cutoff function. Okay, you can see that when the cutoff is larger and larger, this rate will become slower, right? So when we combine them and optimize over beta to find the optimal bound, then we have this bound for my sequence, my functions. Okay, so the sup over this thing is going to be smaller than these two terms. Okay, so this is our error estimate. It's going to be smaller than these two terms. So now the question is, how does m depend on, say, omega? So we can observe that to achieve an order error epsilon, right? So the order of the error to be epsilon. So the first term, let's say, is order epsilon. Then we need this condition. Then if we substitute this here to get rid of the t, we find that m is actually omega epsilon to the minus 1 over omega. Okay, so obviously when omega goes to 0, that means when memory goes to longer and longer, this number of nodes required to accommodate for this memory increases exponentially. Okay, so this is very much similar to the so-called curse of dimensionality, where the number of nodes in the neural network, not in the neural network, but let's say in the polynomial approximation, they actually increases when dimension increases and increases exponentially. Here, the exponential dependence is on memory. Okay, so therefore we coin this the curse of memory. And this is what we can make precise in the linear RNN case. Okay, so to summarize the approximation results, our formulation will be to approximate linear functionals by linear RNNs. Okay, and the first result is a universal approximation theorem that tells you even if your linear functional is not assumed to come from any linear dynamical system, we can still approximate it uniformly in time and also uniformly in state. And the second result, in some sense more interesting, is that we can actually define, we can prove an approximation rate, which relates the rate of approximation with smoothness and memory. So the key insight here is that there is curse of memory in approximation. Okay, so very importantly, this is not the same as the explosion and vanishing of gradients in recurrent neural networks has been studied in a very interesting work here, and also other this reference and also other references. This is not the same because this is not about optimization, right? It's not about training. It's about the architecture, RNN architecture itself, that gives its property that it is very difficult to approximate certain functions with long memory. And here we can actually make this precise. Okay, so this sort of paints the usefulness of going to this simplified linear regime in continuous time. Okay, so for the remaining of the talk, we're going to switch gears and talk about optimization. So we said that, okay, there are some functionals, okay, they are easy to approximate than others, and what's really making a difference is memory, and there's a curse of memory in approximation. Now we're going to see that in optimization, a very similar picture arises. So to motivate this example, we can think about what is the optimization problem at hand. Okay, so we can think of this as basically minimizing the distance between my true target functional and my this RNN functional, right? Which depends on C, W, and U. I'm going to take the mean square error, so the square, and also the mean with respect to the X. So X is your input signal. So these are some distribution over paths, which I can write it out like that, right? So we use the Riesz representation. So rho in some sense is just a representation of H star, okay? And H hat actually also emits a representation, but in terms of this kind of exponential sum, okay? So in some sense, training is basically adjusting these parameters so as to approximate rho. Okay, and we're going to study the dynamics of doing so. Now, of course, if you want a sequence-to-sequence model, then you probably cannot just consider one particular time, t. You have to integrate over time as well. But we're going to consider the simplest case, just one output. Okay, so the gradient descent dynamics is, of course, to apply this gradient descent to each of these parameters, C, W, and U. Okay, so why are we interested in this problem? Let's look at some motivating examples. I'm going to train gradient descent on the linear setting, linear dynamical systems, and learning mostly linear functionals. So first, we can give a linear functional that is parameterized by this rho, so whose Riesz representation is a nice kind of exponentially decaying function. Okay, all this is one dimension. And then you can see the optimization is easy. Okay, so trains very well by gradient descent. Now we're going to consider a second problem where this Riesz representation of my target becomes a Airy function. So it is not at all obvious, whether a linear dynamical system can represent the Airy function's kernel, right? But the kernel in the form of Airy function. The Airy function is an oscillatory function with a decaying part as well. So we're going to apply this, and we've tried to learn this Airy functional with my recurrent neural network. And you can see that you run into problems. Okay, we observe this very long plateaus where the loss is not doing anything, it kind of just flattens. And then you will drop first and then flatten. And after a while, it will drop again, and you will flatten for a very long time, and then you will drop again and flatten. It just keeps doing that. And I want to emphasize this is not just for linear functionals and linear RNNs. Here we choose a actual, you can think of an actual RNN implementation application where you try to learn a forced Lorentz dynamics system. Okay, in this case, I think we use the nonlinear RNN and also nonlinear functional. So there's no Riesz representation for this nonlinear dynamics, and you can observe the similar features. Okay, you have some plateauing and then decay. Okay. So our goal is to understand what is the source of these plateaus, which is kind of more precise than vanishing gradients, because not only does it vanish gradient, we can also how does it have this plateau drop kind of shape, right? And what is the length of this plateau? We want some more precise description of the dynamics. Okay, and this is what we're going to do. We're going to do some fine-grained analysis. And of course, we want to simplify the setting as much as possible. So we're going to introduce a few simplifications. So for those of you who are not interested in the exact details, you can just skip forward this part. So what we're going to simplify is, first, we're going to take X to be the standard Wiener process, so that the expectation can be evaluated precisely, exactly using Ito isometry, right? So the expectation of this square is just the integral of the square. Okay. So this simplifies things. And then the next thing is we're going to take D to be 1. Again, in the linear case, this is enough. And T go to infinity, so that we don't have a particular time T, but just a really, really large time. Okay, so now we end up with this function. This is the loss function. And finally, because this loss function has the exponentiation of a matrix whose the gradient, right? You want to do gradient descent analysis, the gradient is very hard to handle. So we're going to take a diagonal approximation and write the gradient as the minus diagonal of some vector, which is positive entries. And since we diagonalize everything, there's really no difference between C and this vector B. Oh, by the way, B is just going to be, B here is just one column of U, okay, because it's one dimensional. Okay, so there's no difference, so we can just combine B and C into one vector A, and then we can write this sum as basically a sum of exponentials. Okay, and we're going to basically focus on this problem, which is minimizing over A and W. Both are m-dimensional vectors, W being positive, against some target functional representation rho. Okay. Okay, so once we have simplified into this case, we can already see where the plateauing behavior comes from. Okay, at least heuristically. What we can do is to just perform, taking gradients with respect to each of my parameters and look at what is the form of the gradient. And let's just look at the second one because the first one is a similar form. Okay, so the second one has two terms. One is the exponential term. Okay, so this actually decays exponentially when t is large. And then there's a residual term. This term is basically how different is my current approximation, right, by my RNN versus my ground truth target. So when does plateau happen? Plateau happens precisely when the gradient is small, but the J, the loss function, is not small. That means that this residual term cannot be small. This residual term is large. At least its integral is large. Okay, the integral norm is large. But this integral, or you can think of it as inner product, this integral should be small. So when can that happen? So this happens precisely when the residual is large only when t is large. Because when t is large, then the exponential term is extremely small, right? It's exponentially small. So if the residual term, which basically is the error incurred, is only happens when the time is very big, then there's no overlap between these two functions. And if you take the product and integrate, this is going to go to 0. And when is the residual term only large when t is large? That's precisely when you have a target function that has long-term memory. Okay, so this again connects memory precisely to optimization difficulties. Okay, so now let's make this a little bit more precise by saying what kind of rho I really want to look at. Now we're going to build memory explicitly into this target function rho. So we're going to consider a target function that consists of two parts. The first part is a rho bar. The rho bar is going to be a nice exponential sum form that's very easy in some sense to approximate using exponentials. So here you can see that, okay, rho bar is just a very nice and decaying exponential, okay, or sum of exponentials. And then the second term, rho, 0 omega, as the name suggests, omega, is going to be related to memory, as we said before. So what does omega look like? What does this term look like? This term basically looks like this, right? So rho 0 omega is just the shifted form of a template function rho 0, and the template function just looks like this, right? It's just some function. Actually, we have a precise description. Basically, the function says that its norm is well defined, right? Rho 0's norm is well defined, and the omega just shifts this function to the right. Okay, and the center is 1 over omega. Okay, so when omega goes to 0, you can see that the combination of this two, which is our ground truth, it has a larger and larger memory component, right? Because this part is non-zero. When shifted to the right, this is going to cause a residual. Let's say if my current approximation is just on row bar, then when you shift it to the right, the residual becomes further and further, larger and larger t. So you have gradient vanishing, as you said before. Okay. So this is the setup we're going to employ, and let's see what we can get out of this. First of all, you can see that we have this case is at least one very precise case where we can demonstrate this plateauing behavior happens. So before that, we said that, okay, plateauing behavior happens sometimes, it doesn't happen other times. So when does it happen? Okay, so here, this is exactly when it happens. We can show that if you take the form as before and you train your RNN on it, if omega becomes larger and larger, right? So, sorry, omega becomes smaller and smaller, so 1 over omega becomes larger and larger, the plateauing time actually increases. Okay, so now the rest of the goal is to have a concrete characterization of the dynamics. So in particular, we're going to do 4 things. First, we're going to show that from the landscape point of view, right, there's a lot of points that are in some sense equivalent to approximating the first part of the function. So A star W star is the first part of the row bar. Okay, and then near all of these equivalent points, we can show that this loss function is high, right? Because there's a component you're not approximating, that's the row 0, and that component is not small, it's just far away. Okay, so J is going to be bounded away from 0, but this gradient J is going to be small as you decrease omega, so you increase the memory. But this already shows that your loss function is going to plateau at the large value. Now, finally, we can show that the escape phenomenon happens because this the Hessian, okay, of this at this point is going to be almost positive in the sense that it has large positive eigenvalues and small negative eigenvalues. This negative eigenvalue is going to go to 0 very quickly as your memory goes to infinity. So therefore, there's always a chance to escape. Actually, you will always escape, but just that the escape time becomes longer and longer. So with these precise estimates, we can then estimate the time scale at which the escape happens. So basically, there's time scale at which the plateauing happens. And this relies on a local linearization of dynamics, standard practice in dynamical systems theory, that we can derive a time scale. Okay, so then we'll just briefly state the results that we can show here. So first of all, the first result is not necessarily interesting. It just says that there are many points that are equivalent on the landscape. Okay, this is kind of obvious because you can rearrange your A's and W's, and you can always approximate the same function, right? And you can, so basically all of this is just saying that there's many points that are equivalent to approximating the first part, the row bar. Okay, and this forms a manifold. Now, yeah, so okay, so now the first part of the result will be on loss and gradient value. So the first proposition is that for any point that is equivalent on this manifold or this set, J is going to be bounded from below by something that's independent of omega, independent of memory. So J is always going to be suboptimal. Okay, and next we basically show that although this is suboptimal, the gradient is going to vanish. Okay, so this result just says that the gradient is going to vanish as your memory goes to infinity. Okay, so the omega goes to 0. And further, we can have an exponential rate of vanishing if my row 0 is of small support, right, compact support, a Gaussian tail. So this already tells us the plateau behavior, right? This is really made precise. Now, how does it escape from the plateau? And this is the most involved result, is to show that the Hessian actually has a structure that it has some eigenvalues that are positive and order 1 as your increased memory. Whereas the other eigenvalues are actually converging to 0 as you increase memory, but some of them are actually negative. Okay, and the rate at which they converge to 0 can again be quantified again using again exponentially. Okay, it's going to go exponentially to 0, but at any finite omega, okay, under some technical conditions, you're going to have negative eigenvalues. So that means that after a very long time of plateau, perhaps exponentially long, you can still escape, which tells you that this escape phenomenon that we observe in practice. Okay, so then we come to the main result. So from all of this previous one, we can then perform a local linear analysis to show that if we consider the gradient flow of my loss function, right, starting from at or close by a point equivalent to the first part, the rho bar of my loss function, then under some technical decay conditions, again on rho 0, so which is always satisfied if your rho 0 is so your memory part is going to be compactly supported or fast decay, but it's still going to go far away, right? So the entire rho is not going to have fast decay. Okay, so with that technical condition, we can then immediately show that the dynamical system actually gets stuck. Okay, it gets stuck in the plateau, and we can actually precisely quantify the time scale to get an estimate. And you can see this estimate is going to be exponential in omega, in the memory. So this should look familiar to you. This is another facet of the curse of memory, but this time not about approximation, but really in optimization. And it is more precise than the generic or general, so that's good. But sometimes you also want a more precise description of what is it really is happening when you say the gradients vanish. And here is not about initialization. Okay, this is about actual dynamics. Okay, so let's try to numerically verify our result, and before we conclude. So first prediction we had is the log of the plateauing time is going to be a 1 over omega for omega small. That's the memory, right? So then we can show that it's in fact linear. So this relationship is correct. And furthermore, the parameter separation time, which is the time the parameters take to separate away from rho bar to try to approximate rho bar plus rho 0 omega, that again has also exponential increment. So getting the plateauing region is going to increase exponentially. And furthermore, you notice that our analysis is mostly done in the simplified case of diagonal matrices, linear and various gradient flow. So, but here we can show that even in more general cases, this precise situation we identified, which links explicitly memory and optimization dynamics, is generic. But however, we cannot do it analytically easily, so we're going to do it numerically. So for the full matrix case, so non-diagonal, we can apply SGD, and you can show this exactly the same kind of plateauing behavior happens. So this target functional is the one we had before, right? So the two-part rho bar plus the memory term. And then similar things holds for if you replace the linear activation by a tanh activation. So this is the actual neural net that people use in practice. It also happens, so it's no longer a linear network. And finally, even when you don't use SGD and you use like Adam, you're gonna still run into problems. Okay, so Adam significantly improves upon the SGD by momentum, having momentum. Actually, in the paper, we also make precise how momentum actually helps to reduce the plateauing behavior. However, the plateau will still be there. And as you can see, the plateau will still be here. And if I further increase my memory, this is also going to get worse. Okay, so this holds for general cases. So our simplification is representative. Okay, so to summarize our results for the optimization part, in the formulation, we're really studying the gradient flow of linear recurrent neural nets, okay, and approximation of linear functionals. In this case, we basically identified what we should consider as a representative situation of memory and its interactions with dynamics that are one realistic, that represents a lot of things we see in practice, and also amenable to exact analysis. Right? In this case, we have two parts. Rho bar is the easy to approximate part, okay, and the other part is a memory part. And as omega goes to 0, the memory goes to infinity, right? So the memory shifts to the right. And then this will let us analyze the precise dynamics near one of these kind of pseudo stable points, right? Because if this vanishes, of course, rho equals to rho bar is a global minimum, right? Okay, so this results in plateauing behavior, and we can derive the plateau time, which we can verify by experiments. So the key insight here is that cursor memory again comes up in optimization, in that the plateauing time is an exponential function of memory. And this is a more precise statement than vanishing and exploding gradients, because it captures the precise dynamics of the system. And the dynamics is really on the interaction of RNN structure and the target, both of which have dynamical structures. And this kind of couples them and make a statement that depends on both. Okay, so with that said, let's conclude this video. So in this work, we basically analyze the simplest, in some sense, the simplest possible setting of recurrent neural networks and its usage in modeling input-output relationships. It's a simple setting, but we get some non-trivial behavior, and the overarching theme of this entire thing is cursor memory. And it happens both in terms of approximation, which concerns the architectural aspect, and optimization, which concerns the training aspect. And both of this memory plays a role that is significant. So in some sense, this puts the heuristic observations in practice about how it's hard to use RNN to learn some system with long memory. We try to make that into precise mathematical statements. And in this linear setting is a start. Okay, we can then make all of this very precise. Okay, and future work, of course, there's a lot of things that remains to be done. For example, we only discussed approximation optimization. So what about generalization? How does it affect, how does this dynamical aspect differ from the static setting? Okay, so that's worth investigating. Actually, there's a lot of recent work on this from other angles, let's say, active learning. And then we have this linear to nonlinear. So far we prove everything in the linear case, right? So how much of this still holds for nonlinear case? This remains an important challenge. We have some preliminary results in this, but this is a much harder problem. But again, we want to emphasize that what's really new here is not linear to nonlinear, but really linear, static to dynamic. So that's the first part we want to address. And finally, we talk about RNN, but there's also other sequence models like LSTM-GRU. So all of this are RNN variants, and to understand how things change in that area is very important. And also transformers and CNNs, there's other ways to, not RNNs, that to use to do sequences to sequence models, and to understand really precisely what's the difference. And I want to say that the framework that we introduced here is actually a very simple framework that is hopeful to try to illustrate exactly what's really different about these things. I mean, in the practical literature, you see people say that okay, transformer is the thing to do now. LSTM is dead, and then also there are the statements in the reverse. So maybe this linear setting, or this approach of continuous time and linear setting will gain some insights into precisely when is one better than the other. Okay, so hopefully the next time we have this meeting, I can tell you a little bit more about these things. Or maybe people already done it in this meeting, so I'm happy to find out more. And finally, we discussed this plateauing behavior. So the natural question will also be, how could we design algorithms to overcome this? Okay, and that's again an interesting thing that should happen after we get a good understanding of what's going on. The eventual goal of this entire project, this series of projects to come, is really to have a good theoretical basis for the interaction of dynamical structures in models, right? So this kind of RNNs, dynamical shape, right? Dynamical structure, and also data, the functionals are being used to approximate. I think the latter part is the most important when it comes to the contribution, potential contribution with this approach, is that very often, if you only talk about analyzing RNN without mentioning to what is the target is trying to achieve, then this is not the whole picture, right? How it behaves really depends on what it's trying to learn. And this unified framework could be something that is useful to really uncover the coupling between models and data. For example, in NLP applications, it's very hard to put a concrete description of what is the data with long memory or short memory. But in our case, once you go into this more mathematical framework, these notions can be made more precise. Okay, so the eventual goal is to really understand what is it that we need to understand for machine learning for dynamical systems. So with that said, I come to the end of my video. The preprint is coming up. I should be able to release the link during the live talk. And if possible, before that, I'll update in the video description of this video on YouTube. And the live talk time is going to be this time, which I'll give a combined talk with my collaborator, Weinan, on the various aspects of machine learning. So I'll talk about 4, and there will be also other talks on machine learning via dynamical systems and machine learning of dynamical systems. So stay tuned. Okay, so thank you very much, and I'm happy to clarify any questions.